Thank you very much. Yeah, I'm going to use this.
Okay.
Here we go.
Right.
Here we go. Let's see. Oh. So the video is not working on the slides. Normally you would see the cars moving around here on the front screen. So I'm Chris Benson. I am going to talk to you a little bit about deep learning and digital transformation. There's the video. It took a moment there. So almost didn't make it today. I'm from Atlanta, and we had a close call with a hurricane, and I had a broken foot. So forgive me as I hobble around the stage here talking. I have a cast boot on. This is me. I just left Honeywell, where I was the chief scientist for AI and ML for one of their global divisions. I built the capability there. And before that, I was at Accenture. And then I have some other activities around the AI world, such as a podcast and deep learning group. And so I do a lot of talking about these topics with different groups. I had my first start quite a ways back on this. For those of you who are old enough to remember, it's the original IBM PC when it came out. Did my first Hello World on that, and been doing data science and computer science ever since. So I got introduced to artificial intelligence before most people out there. It's been 26 years, and people are like, really? That far back? And that's because there was this plane that was built in the Atlanta area. And some of you may recognize it. It's the F-22 stealth fighter. It was built in the Lockheed, Georgia plant, just outside of Atlanta. And they had a serious situation when it was still a prototype. There was a test going on at Edwards Air Force Base in California, and the plane was supposed to prevent the pilot from being able to crash it. So they were testing the avionics, and things did not go quite as they planned. The good news is the pilot was fine, and after skidding fiery down the runway, he got out. But this somehow led to me getting into AI, and that was because this particular man was responsible as the engineer to go figure out what happened, what went wrong, and why did that. And the reason I came into the story is this particular guy was my father. And so for about a year, as he was dealing with it, he would come home from work, and I was a college student, and we talked about neural networks, which was the technology he was using of the day to try to solve it. And I developed a passion, and thereafter, it led ultimately to where we are today. And so I wanted to share that, in that I've had a long time as an engineer to think about how neural networks solve the problems that we're dealing with today. And so I want to talk about, since we're talking about how does deep learning affect digital transformation and what is digital transformation, I want to real quick cover that. It's common misconceptions there. It's not a channel, because people often think, oh, a digital channel, that kind of thing. And it's not a project. It's not something you go off and stick a budget on and go do. It's the purpose of digital transformation is not to digitize an existing state, but to completely reimagine what kind of business model is appropriate to solve your problem. So if you were starting on your existing business today with the technologies that you have, and you were saying, how would we create this today from scratch? That's what it's about. So what we're really saying is that it's all about innovation. It's not about optimization, and that's a really common misconception. A lot of companies will go fund digital transformation projects, stick a budget, and they're trying to basically change something they already have in place with technologies. So the thing about it is digital transformation is itself going through a massive transformation right now. And that is because of AI. And as we talk about here, it's kind of led through this, in that we've had the cognitive revolution, which happened 70,000 years ago, agricultural revolution 12,000 years ago, followed by industrial, digital, and now the AI revolution. And they've gradually been changing society more and more. But now as we're getting into AI and it's impacting everything, we're talking massive changes to social, cultural, and economic interests all over the world, and it definitely affects digital transformation that all of our businesses are going to be going through. So digital transformation is at the very heart of this AI-driven change going forward. Artificial intelligence is already changing how these business models are being reimagined. So you could think of it as AI is the technology we're talking about, and digital transformation is that strategic process. And fundamentally, the technology is changing the fundamentals of how you apply the strategic process going forward. So I wanted to put this in a little bit of context. this lady is essentially the CTO at the United Nations, and she talks a lot about this in terms of how we should think about ourselves as technologists in this AI and digital transformation world going forward. And the ramifications, they're good and bad, that we all see in the news. And what do we need to do? What does our businesses need to do to transform ourselves going forward? If you look at the last 20 years, a lot of change has happened, but that's nothing like what we're going to see in the next 20 years, next 50 years, 100 years. We're going up an exponential curve with this. So you could think of that AI might be the last major innovation that humans are creating, because going forward, we're going to be using the AI itself to create those next innovations. And so you have a question there that we all have to answer as businesses of, the obvious labor things. We talk about jobs and things like that, but there's amazing great sides, amazing upside, and some downsides to contend with. So ultimately, the objective of digital transformation is going to be to try to figure out how to cope with the downsides while taking advantage of amazing upsides going forward. So this is the AI-enabled world of digital transformation going forward. So I've been throwing around AI a lot, and sometimes that can be hard to define. So can we define AI? Well, that's easier said than done, because if you ask 10 different AI experts to define AI, you're going to typically come up with 10 different answers. And so how do I know this? Well, because Adobe recently did this, and I was invited to be one of those AI experts that they polled. So we had a group in a think tank in New York City that was broadcast, and it was funny. You put all these people that are supposed to know all about AI, and the thing was, we were unable to define it. Every one of us had a completely different answer. So I say, I'm going to kind of share what my definition is, and it's perfectly fine to not agree with me on precisely, because there were at least 9 other AI experts in that room that didn't agree with me. And each one of them had the same dilemma. They all had 9 people that didn't agree with them. So I define AI in a very narrow context personally. I consider AI to be a marketing buzzword, and it evolves over time. It was the neural networks that my father was doing in the early 90s was AI. There were other things that were attached to the label, and as time goes on, different technologies get attached to that AI label. So it evolves. It'll probably be, my definition will evolve also. For 5, 10 years from now, it'll probably be a bit different. So these days, I take the fact that AI being a marketing buzzword, and obviously digital transformation is too, because that's evolving. And so I consider AI simply to be deep learning. There are other technologies you can argue are in there, and that's fine. But I think this is what's really driven this massive surge over the last few years. So I realize that not everybody will agree with my own definition. Princess Leia's looking pretty rough there, I think, with the stormtroopers behind her. But I did also want to share one other thing that's just an aside as we go on, and that is that we did all agree on exactly one key principle in that group of 10 people. We all agreed that you start with the customer, no matter what industry you're in, what your project is, where you're applying, and you work yourself backwards to the technology. So we couldn't agree on what AI was, but we could agree on what you do with it when you're trying to apply it. So what is deep learning? I want to talk about that for a moment. It's really modern AI that is working today. And it's an approach to machine learning that's driving the current artificial intelligence revolution. And it's an approach to machine learning that draws its inspiration from the human brain, statistics, and applied mathematics. So, and by the way, the quotes here are from the seminal textbook in the field, which is called the Deep Learning Textbook, just to note that there. And they note in the textbook, which is probably many of us understand here, that the things that are driving this at this point are the facts that we have new techniques every year. And right now, we have new techniques almost every few months. Giant data sets that are just getting bigger and more available, and obviously more powerful computers, whether they be cloud-based or NVIDIA supercomputers or whatever you want to have. And so what that really means is that you're talking about the modern application of neural networks to achieve the machine learning goals that you have. So you're learning from data without explicit programming. And that is neural computing. And this is a term you're going to see more and more in the years ahead, because I was recently at the NVIDIA GTC conference back in, I guess it was February now, and I noticed that their CEO was talking a lot about neural computing, and it's kind of a shift in the way we're thinking about programming. Instead of being explicit, if this, then that, go through a loop, I have to think of everything as a programmer, we're now going to start having models that do a lot of that decision making, and we accommodate those models in day-to-day programming. This is a huge shift in computing going forward. So this is kind of how I see deep learning as AI fitting into the space. It is one type of machine learning. It's not the only type of machine learning. There are many other algorithms out there. Some of them, people will argue, also take part in that AI world. So obviously I have the bias that I've already disclosed. And then those fit into the larger combined world of data science and computer science. So one of the things we tend to talk about deep learning a lot without, a lot of people don't really understand why. Why is it this? We keep talking about deep learning. It's so popular. You hear about it and everything. What is making deep learning such an amazing tool for us, or at least why are we talking about it so much? So I want to talk about what drives it. And this guy here is excited, I can tell you. And that is that you can precisely approximate any continuous function. So maybe not this crowd, because it's a fairly technical crowd, but a lot of people, they see that slide and they start to fall asleep and go, really? That's your big reveal right there? But it's a pretty powerful statement, because you're basically saying that nearly any imaginable process involves computing a function. And if you can approximate that function with neural networks, if that's possible, that means you can apply it to a lot of different problems. So this is huge. Neural networks are somewhat universal. And that means that deep learning is a universal approach to solving complex problems. So Homer's pretty happy about that, but deep learning is currently, as you're probably aware, right at the very peak of the hype cycle. It's magic. It can do anything. It can solve any problem in the world. I just said it was the universal toolbox, didn't I? But we'll talk a little bit in a few minutes about what it's good to solve and what things are maybe not so perfect for it. And having said that, I would recommend that keep in mind that it's at the peak of the hype cycle. Ignore the hype. Just ignore the hype on it completely and focus entirely on the practical applications. So let's talk a little bit about how this technology, how deep learning in the context of digital transformation is being applied out there in industry. So probably the first mainstream stuff was Google several years ago kicking off and talking about it. And that was kicked off by the idea that he noted that the last 10 years have been about mobile first, and we heard that so much. But the next 10 years, we're several years into that, is all about AI first. And so as they look forward, they have been, and we've probably experienced it, if you have Gmail and are doing Google searches and stuff, those services have been evolving very rapidly. And so you are seeing them go through all their services and implement AI, neural network models, wherever it makes sense to help them along. And that's an ongoing thing. And everybody else in the world has followed suit on that. It is becoming one of those things that everyone realizes they really need to do now. About a year and a half ago, close to, I guess actually it's been over that, it's been over 2 years ago now, this CIO was commenting that if you were looking back 3 years and you decided to get into deep learning then, you would have spent an enormous amount of money and effort and time with limited results. But if you were to wait 3 more years, you're going to be hopelessly behind. And I've had that slide for a while in various talks, and I found that as we're approaching that 3-year mark, I think he's dead on. I never knew if his timeline was right. I agreed with the sentiment, but I think his timeline is right because everyone's doing it now. Everybody is trying to figure out how to apply models. So if your company isn't, then you probably need to be thinking about that. Because in these years ahead, we're certainly going to consume and will probably be creating artificial intelligence at companies throughout the world and machine learning in the form of microservices. It'll just be normal programming, APIs that we're used to having. It won't be anything distinct and magical. So see, these are some of the more common use cases. And well, let me pop back. Just a second, I hit the wrong button there. These are some of the common use cases, and this doesn't even begin to cover all of them. This is a tiny smattering. Kind of by line, we're talking about kind of security, marketing, some of the different computer vision applications and speech recognition, obviously transportation, with us talking about automated vehicles everywhere, and healthcare is huge, and then financial. And as a matter of fact, these days, really everything in the securities market is regulated by these models. Some of these crashes that we've had recently where it drops hundreds of points in a few minutes and pops straight back up, all of that is computer driven by these types of models as they're learning to do it better and better. So Andrew Ngee in Harvard Business Review also put this out as just a basic way of talking about some of the use cases that you can apply these technologies to. And he did it in a very simple, like, I got a picture, or they're human faces, and that's photo tagging. So you can take a look at that, and I'll make the slides available later on. But I really want to talk about what is today's AI good at. It's really good at solving complex but very, very specific problems. And oftentimes, it can do that far better than humans can. And that's where you're seeing giant strides in things that we see even on CNN about what certain systems are able to do so much better. Radiologists the last few years have been in a hard place because the CNNs of today, the convolutional neural networks, which we'll talk about, can analyze those images so much better than a human can, and that's being spread out. So what is AI bad at? It's really bad right now at problems that involve creativity or that change or evolve continuously. And that may not always be the case, but right now it is, ironically, it's a lot easier for a neural network to go and do the job of a radiologist, which is a highly specialized field, versus if you were back before the agricultural revolution and you were a hunter-gatherer, and there were so many different things that you needed to be able to do to survive on a day-to-day basis, neural networks would never be able to handle the complexity and diversity of all those today. So the real power equation going forward is humans plus AI. You have a bunch of different use cases. There's autonomous vehicles where you're essentially delegating that. Robotics, where it's a combination of collaboration and delegation. Interactions through either augmented reality, mobile, or conversational interfaces. I don't know about y'all, but I have both Amazon and Google in my home listening to everything I say. In some cases, the same device. Both devices are in the same room. So that is the world going forward. So really, what AI is going to do in the near future is give us superpowers. You'll have the ability to work with that AI to do your job, but so much more productively than you ever could have done it before. So we talk about a world transformed. We're all familiar with Google's automated vehicles and the profound changes that's doing, that's creating in industry. It's moving from cars to flying vehicles to trucks on the highway. You name it, that entire industry is being digitally transformed through this technology. This is kind of a joke of mine that I found and I like, and it's that, are we going to just have bots? Everyone talks about bots. When I was at Accenture, we talked about bots all day long. I got to where I couldn't stand bots anymore because so many companies are creating bots for anything they want to do, which assists the people, their customers, their employees. And as we do that going forward, it's going to affect all of our lives in a profound way in the fairly near future. Gartner has estimated that by 2025, half of our primary healthcare needs are going to be handled by bots. These technologies are already out there. They're getting much, much better very, very quickly. And so you're going to go to your iPhone or Android as your first mechanism for solving whatever your ailment of the day is. And you'll only go in and see a doctor once you get passed up. You'll no longer start with a primary care physician. You'll start with the bot and then work your way into that. And you'll get faster, better service as a result. So lots of bots. We're all building chat bots. Google's DeepMind is doing some amazing things in terms of cancer treatment. And you're also going to find that even in things like stopping violence, this is a system here that is able to, through microphones placed throughout a region, hear gunshots and route police much faster than they could have before based on neural networks analyzing where crime is occurring and giving the dispatchers an early go. So it's pretty amazing. So we've been kind of talking about use cases and how it affects the world. And I want to do a little bit of a deep dive for those of you who may not be familiar with exactly what, and I have this fellow again, apologize for that, and to kind of talk about how neural networks work fundamentally. So you're really talking about creating training that enables generalized predictions using known correct results. And this is called supervised learning. As opposed to unsupervised learning or reinforcement learning, all of which are in the space, but I'm kind of starting with the basics here. As you do that, you have to have, for training to work, you have to have a lot of known correct results. It can often be easily in the thousands, often in the hundreds of thousands or millions of samples that you can say, this is the reality. We have a historical record, And by using the historical record, we're going to be able to train a neural network to do this the way it should be done, based on that historical record. And so once trained, though, from that historical record, a neural network can give completely new things from existing. You can have a new input, and it can give you a completely new output based on that existing generalization, and it's likely going to be right. In a lot of cases, it's going to be 99+% right, which is incredibly powerful. So you're essentially talking about learning from experience here. And so this is a slide that kind of shows a toy neural network. You got a couple of different nodes, and basically you would start your training process by randomizing the weights. Each one of those nodes has a weight associated with it, and it has an algorithm that you put in called an activation function that does something with the numbers coming in. So you have all your data going in is in the form of a number. Those numbers get pushed through, processed by each neuron, and pushed through. They're fully connected from layer to layer. Every neuron at one layer goes to all the neurons at the next. And you push that through, and then every neuron here accepts all the inputs coming into it, has the transfer function, and then activates that back out. And so you could almost think of this as trying to find the lowest error through the entire network to get to achieve your accuracy. And there are different ways of approaching that. So you get to the end, and if you're talking about using backpropagation, which is probably the kind of the granddaddy of the algorithms applied in the space, then it pushes those back using that known correct number, pushes them all the way back through and filters them to the beginning and makes adjustments to those weights, and then it pushes them back through again. It goes back and forth for every row of data you have in your set, which can be millions, as we discussed. And it's getting better and better and reducing that error down. And eventually, after what you're essentially doing is this search to find the right answer for that, you're going to get to a final neural network. And if you notice, the arrows represent the weights that are being applied. And you could then take this trained neural network, stick it out in the real world, take in new data for that same kind of problem that the network has never seen before, and it should give you a very, very good answer for that. And that's the fundamental way that feed-forward backpropagation works, which is kind of where everybody starts. And so you could think of this as a way of representing all these as a set of hierarchies. The layers are each taking what comes in before and creating a new node in that hierarchy. And so it's really a set of hierarchies that the neural network creates. They're each one conceptual at a different layer. So these are the common architectures that you're going to find. We just talked about feed-forward networks. There's also, for computer vision and for now other applications as well, convolutional neural networks are amazing. There's a new one that may replace them called capsule networks that a lot of us are focused on at this point. Recurrent is great for sequential problems that you're trying to solve. And generative adversarial allow you to generate new data by having neural networks essentially kind of fight it out. One creates things, and the other one has to discriminate whether or not it's real or not. And you work your way into new outputs through the two of those working against each other. I'm going to go pretty quick because we're short on time. Fundamentally, a convolutional neural network takes a big picture and breaks it down into what you could think of as features, and eventually it can feed that into that feed-forward network and identify what that is. Going beyond that is beyond the scope of our time, but fundamentally you need lots of data and you need lots of computation. So if you're going to invest in deep learning, you want to have all of these are kind of really startup concepts that you want to really do, because deep learning is definitely an area where you're not going to just do this and you automatically get results. You have to search your way into getting where you want to go. So startups or big companies that have a startup mentality within a team tend to do better than others on getting there. And there's a bunch of questions. Most of these are very typical data science questions that you probably have already used even if you weren't doing deep learning, in terms of how you're going to get into this and what kind of things you need in place. I'll let you take a look at that as I move on. And this comes back. I mentioned earlier that we would come back to this. You have to start with the fundamental problem you're trying to solve and work your way into what is the right deep learning solution that you're trying to get to. So you want to analyze the problem statement. Can you solve the problem with simpler, less expensive tools? Because sometimes deep learning is not the right solution. There may be other machine learning solutions that are much quicker to get to without the investment. So deep learning can be expensive to scale. Once you get into large data sets and processing on those for complex problems, your training costs can quickly spiral in. I know somebody who accidentally spent $100,000 out of budget. I think he had a $10,000 budget for a small project, and he left something overnight and came back and he had spent 100 grand. So that was fairly painful. It really requires a strategic investment from your leadership team. And you really need to recruit the very best people you can find and train the people that you have so that you can get into this. That requires that you have a learning culture, and you need a mixture of different skills, not just data scientists. The teams that I've run have been very eclectic in terms of what their capabilities were. And that means you need someone who knows deep learning. Not all data scientists are familiar with it. So you need to make sure you have your data and have your data strategy in place. You need lots of data, lots of computation, as I noted, and then going through with the, sorry about that, I think I'm going, you need an executable AI strategy as a prerequisite. If you don't have your if you don't have your data strategy for your AI strategy, then you are going to feel a lot of pain. And if there's one thing that I've run into more often than anything else with other teams and with customers, is that they didn't figure out their data strategy ahead of time so their AI strategy would work. So that's where most organizations fail. So get that in order, have a process. It's really no different from any other data science process. Feature engineering, model selection, model training. Make sure that your software and systems are able to do what it is that you need them to do, and that you have a deployment strategy. And this is really where I want to finish, is that when we get to deployment, things get difficult. For me, when I was at both Accenture and Honeywell, we had a fairly standard environment that we were able to operate in. The usual cloud providers. At Honeywell, we also had our own hardware that we could use, and we had a bunch of great frameworks with which we could actually go. And we'd use TensorFlow, more recently PyTorch, and some of the others, and it really depended on who on the team wanted to do what, and we could get there. But and that was pretty amazing that those frameworks were starting off with Docker and Kubernetes standard, the usual cloud technologies. But even though your open source tools are democratizing your accessibility to these technologies, when you got to deployment, that is where things got difficult. We would get to where we were deploying to one vendor's edge devices or another vendor's edge devices, and I don't want to call names out, but as we moved from vendor to vendor, we found that we had to completely relearn or re-engineer how we were approaching it. Sometimes we'd actually go back and have to move our models from one open source framework into another one because the vendor B supported it, vendor A supported that one. And so I think if there's one thing as we finish up that I have been hoping for the better part of the last year, maybe year and a half, it's that we would get better vendor support for being able to take advantage of the optimizations that everyone's hardware could do. The people are putting the acceleration in, they're supporting certain frameworks and not others, and so my vision as we close out of rainbows and unicorns is having a deployment environment that allows us to go through less pain, more of a common, unified way. So I wanted to finish this talk as I talk to this particular group and say, I hope that you will go out and those of us who are working in the space help us get there a little bit easier and a little bit better. And we may have some interesting conversations today about that. Having said that, I just want to say I welcome you to listen to my podcast. There it is. And if you have an interesting story, see me afterwards, and we'd love to get you on. And that's it. Thank you very much for listening.
We have time for a question if anyone would like to ask a question. Yes, gentleman over there.
I'm going to get some water as we talk.
Yeah. Go on.
What are the parameters in sizing up the number of nodes, sizing up the deep learning network?
So could you say that again?
Given a problem, how would you define how wide and deep your tree would be? of those?
So when you go back to the process slides, and I know given the time, I will skip through them very, very quickly.
Sure, sure.
But when you're analyzing the problem, and you will realistically, you will come up with a candidate which is probably very much like somebody else before you has. We do a lot of transfer learning. And so you'll say, I have a problem, how have people solved that before? You go find a model where people have written about what they've done, and you do that. And generally speaking, if you're lucky, it might work, but more often than not, it doesn't work quite as well as you want. So you keep iterating, and then you start saying, well, what makes my problem different from theirs? And you start saying, okay, I have these layers in this architecture that serve these purposes, so it's an engineering question is what it becomes. It's saying, as I separate the requirements this model that I'm transferring in to utilize did, and I have this problem over here, what makes it different? And then I start adding or subtracting parts to the architecture that allow me to get closer to that set of requirements. And then it's trial and error. You go back and back and back and try until you get there. Does that answer?
Yes, very helpful. Thank you.
All right, thank you very much, Chris.
Thank you so much.
So Chris is going to be around for the rest of the
I will,
day.
yep.
So, and try not to stand on his foot, which I nearly did earlier. Okay,
Thank you very much.